All right, here we go. We're going to continue on with SolidCam. So to date, we have written a drill toolpath and a pocketing toolpath. And today we're going to go into the third major type, which is a profiling toolpath. We're going to open up this file. This is the bottom plate for the QB50 CubeSat for which you're making the side plates. So if you go to SolidCam, you can see, oh, I wrote these too. I'm going to delete those. Hey. Okay, so in another life here, I wrote, if you look in your SolidCam, I've got operations. I wrote a hole path and a pocketing path. Again, we go back to simulate. One thing I didn't show you yesterday was some of the simulation options. There's a whole bunch here. The two we use the most are HostCAD and Solid Verify. So if you look at Solid Verify and you run it, it drills the holes. It looks a little different than the HostCAD. This is Solid Verify is more used for, it's more of a realistic look of what's going on with the part. If you go to HostCAD, you get little coordinate systems and little stock boxes and a bunch of and all of the features on your part. So when we play this, you can see the holes there. But Solid Verify is kind of a real look at what's happening. So that's kind of useful sometimes. Another thing, let's do this pocketing. Okay, so there's the pocket. You can see I'm showing the tool. I'm also showing the path. That's this button here, Show Tool Path. You can see the little orange stuff is the path. That's kind of how it leaves a trail of what it's cut. And then the red lines are the rapid movements. That's where it's going to move at the fastest feed rate that the machine can go. You can take, let's take Show Toolpath off and hit play. You see it's cutting the material out, but you can't see the path. Sometimes that's useful. We could hit Show Holder. We haven't defined the holder, so that doesn't do much. Now, another very, very useful tool is Show Data. So all of this is a visual representation, and that's nice. Sometimes we want to see exactly where that tool is in space. So I'm going to hit this step feature. It's single step mode. And you can see, okay, there's my tool. And if you look at the data, it's feeding really fast. It's got my spindle speed, my step, and it also has how much time has elapsed. That's kind of nice for figuring out how long your program's going to be. But take a look at the Z. It also tells me where I am in Z space. I'm 0.1, above the part. That's my safety distance. I hit the next step. Boom, I just went to 20,000 steep. And now it's going to start stepping around that pocket. Okay? This is a very useful thing sometimes to know where that tool is. So realize that that's there. I'm going to go ahead and run this all the way through, and then you can see this toolpath is going to take 9 minutes 54 seconds. So that's really useful for planning purposes. Okay, I want to show you that. Today we're going to go into profile paths. And what a profile path means is, and you remember a pocket was a closed contour, and it said chew everything out in between that closed contour. A profile in other CAD or CAM programs is just called a contour. You select a line or a series of chains or arcs or whatever, and you say just follow that selection. And it doesn't have to be a closed path. It could be open. Ooh, I got good sleep last night. What's going on there? All right, so let's do one. So we've drilled these holes and we've pocketed these holes out. Now we want to machine out this part. So I'm going to go to Operations, Add Milling Operation, Profile. And I want to select my geometry. So I'm going to select this line here. Okay, notice I've got the arrow saying I'm going to go this way, and it started this line. You've talked about climb and conventional cuts, right? So if my tool is spinning clockwise, which they always are, and I'm starting here and going this way, what kind of cut is that, climb or conventional? (50-50) chance. Is it a climb or a conventional cut? So my tool's spinning right here, and it comes down on this point and starts moving this way. So it's spinning like this and it's moving this direction. Is it a climb or a conventional? It's a climb. Remember, most of the time we want to climb. And the reason is you've got a tool, it's a cantilever beam. If I'm cutting this side, in a climb cut, the tool deflection, the bending of that beam will be away from our part. In a conventional, it will be into our part. So on the climb, it'll cut the part a little bit bigger than it needs to be, and in a conventional, it'll cut it a little bit smaller. Most of the time we want bigger because then we can always go back and cut more off, right? You can't add material back. So most of the time we want to climb. I'm going to show you a couple of pictures that demonstrate this idea. I apologize that they're blurry. So this was a piece of material that we cut out for one of our senior projects last year. It's kind of a dummy mass for their project. It was an 1.5 inch thick piece of aluminum, very, very thick. And we used two tools. We used a rougher and we used a finisher. We used the rougher to hog out a lot of material quickly. It has this kind of ribbed geometry here, which really aggressively rips the chips and throws them out of the way, so you can go a lot quicker and take bigger cuts. Then we used the finisher to kind of clean up the surface, because the surface on a rougher leaves a poor surface. You can see that here. So here's the rougher and here's the finisher. Both of these paths, we did the rougher first and then we ran back with the finisher. Both of these paths were done on the same geometry. So what happened with the rougher was it deflected heavily because we were taking massive cuts. So the magnitude of that deflection was very large. Okay, so as it cut around, that deflection was real big like this. Okay, so then when we went back with the finisher, we're taking a much smaller cut. It came by and it cut just this bottom. You see that? The rougher path is still up here. And it did that, and that shows you that deflection. So the rougher was cutting up here where it wasn't deflecting, and it was leaving a lot of material down at the bottom. Okay? This was fine. We just went in and took a couple of more cuts with the finisher, but it's just a good demonstration of how the tool deflects. There was a lot more material left down here for the finisher to cut off because that rougher deflected so badly. If we had been conventional cutting this contour, it would have been into the part. Okay, so when we cut our finisher path, this finisher would have finished up here and it would not have finished down here, which is bad because we would have had to take more material off this diameter to clean that surface up. Okay, so that's tool deflection. All right, let's go ahead and go around. Now I could go click every one of these little lines, or I could use the auto 2 and constant Z and select. And it was acting slow before, it wasn't selecting for me, but let's just try another one. Maybe it'll figure it out. Let's go, little guy. You can auto select. Come on, you can do it. Maybe it can't do it. Did this to me in the other lecture too. Oh, it's thinking about it. Now it's all hosed. I think I'm going to try that again. Let's start over. Go around, you dirty. There we go. At least it got those. See, it's doing some weird sort of thinking about it right there. Alright, well, if you're not going to play, we'll just go around and select it ourselves. Oh, no. Gosh, it's just not playing right now. Look at it now. It finally decided to do it. Come on. It finally decided to do it. Alright, we've got our chain and I'll accept it. I don't know what's going on here. I feel like it's that SolidWorks thing again. Alright, let's go to our tool. We're going to go ahead and select a tool. I'm going to do a new one here so we can show you this again. End mill. Who's got, let's pick somebody. Alex, what are your tools?
I have a .156 inch drill.
Yeah, well, what are your tool numbers assignments?
11 through 14.
11 through 14. So let's just say he wanted to call this tool number 12. So this is Alex writing here. Okay, we've got a 1/4 inch diameter. That's fine. We want to change our feed. In XY, when it's cutting the material, it'll be 10. In Z, we'll call it 5. Its spindle speed rate, let's go up to 3,500. And we'll check coolant. And call that good. Check this out. If you drag out here, it shows you the tool. It's kind of cool. Alright. Levels. My start level, my clearance level are 2. I would have liked them to be 5, but when I first defined this part, I put them as 2. We could go back and change it, but I'm going to skip that for right now. My upper level is 0. That's good. That's because that's where I put my part. But it's asking me for a profile depth, so I've got to select that and grab the bottom. Okay, got my levels. And now we go into technology, and this is where you get a whole bunch more options than the pocketing paths. So we're going to go into a few of these. First of all, you can select which side it's going to cut on. Now remember, in a pocket, you've got a rectangle. It's going to chew everything out in between. So you don't get to select which side you're cutting on. Okay? Here it's just a line. So we get to decide which side we're going to be on. If you look at the options, you could be right, which is one side of the line, left, which is the other side of the line, or you can straddle that line right down the center of the tool. We do that sometimes. If you're climbing, it's typically left. So let's stick with left. Depth type, you can change your depth type, so you can keep it constant. So you can say, okay, I go down into the material, I go around this line, I go down in a little bit more, go around this line. Or you could do, say, helical, so you could go around and down as you're going. I'm going to keep it constant. You can do one way or zigzag, so as we start around here, you could go all the way around and then go down a little bit farther and go all the way around. If you zigzag, it'll go all the way around and then it'll come back. We don't want that, because if we come back, that'll be a conventional cut. So we don't want that in this specific case, but you might want that. All right, offsets. Now these are going to be for your finish cuts. Notice they're grayed out right now, and the reason they are is because you haven't told it we want to rough it. So if it doesn't think you have to rough it, why would it leave any material for finishing? So we're going to click rough, and then those options open up. Remember, our wall offset is how much we leave on the walls. In this case, our wall is right there. Do we want to leave anything on that wall? In other words, do we want to do a finish cut on that wall? We do, to make it pretty. How about the floor? This floor down here, do we want to do a finish cut there? No, because we've cut through the material. There's nothing left to finish. It's all gone already. Okay? Your rough step down, if you don't put a step down in here, it's going to do it all at once. In this case, this material is like 78 thousandths thick. We could just do it all at once, probably with a 1/4 inch end mill. It could probably handle it. But, yeah, let's go ahead and just leave it. Well, no, let's leave it. Let's leave it. Your finish pass, you can pick how many finish passes you want. So it's going to leave 5 thousandths to finish. But you don't have to do that 5 thousandths all at once. You could do that 5 thousandths in 2 steps, let's say, 2 finish passes at 2.5 thousandths each if you wanted to. I'm going to leave it as 1 for now. Extension overlap. So this field, in conjunction with a field I'm going to show you in a minute, lead in, lead outs, will help you avoid what are called blend marks. So if you don't select these things, the tool's going to come down somewhere, probably where we started it. But let's say it came down in the center of this line. It's going to come down here, right on top of it, and plunge into the part. And it's going to wobble a little bit, just by a couple of thousandths. Then it's going to go around and cut all this outside. When you're done, all of it will look real nice, except right where it came down in there, there'll be a little mark. It'll only be on the order of 1,000th or 2, but it'll be noticeable. You'll be able to see it and feel it. If you don't want that, you need to use this extension overlap and another function called lead in, lead out, which I'll show you in a second. This extension overlap, you can see the picture right here. What it tells you is if the tool is going to come in right here and come around, and it would finish there. But if you put the extension overlap in, it'll go around and it'll keep going for as long as you asked it to here. And that way it doesn't start and stop at the exact same place. It kind of runs over that start and stop. So let's put one of those in, and I'm going to make it kind of radical so you can see it. I'm going to make it like 1 inch. You wouldn't normally do that. You really only need to go about the radius of the cutter, and it'll be good enough. Step downs. So you may not want to finish your whole wall all at once. You may want to step down just like you did when you were roughing. In this case, the material is so thin, we can just go ahead and take it all at once. So I'm not going to put a step down. It's going to do it all at once. There's other options, but those are the main ones that you're going to use. Advanced, again, there's other options, but you're probably not going to use those very often. So that's our technology. All right. Any questions on any of these options? Your link. These two are your most likely you're going to use here, which is your lead in, lead out. If you don't have a lead in, lead out, the tool's going to come right down on this where we started. Just plunge right down in the material and get going around the profile. Maybe you didn't want that. You didn't want it plunging down and wobbling and bumping into your finished material. So what you can do is you can define a lead in, lead out, which will say, okay, don't start right there. Start out here somewhere and smoothly transition in around. Okay, and that's what the lead in, lead outs do. There's a whole bunch of different ways to do it. Normal, it'll start out here, jog in, and then start coming in. Arc, it'll do an arc and then come in. Tangent, we'll do a tangent and then come in. Let's do the tangent one. Doesn't really matter, but let's do that. So click in this field, tangent extension. That's how long it's going to be before where it's going to start out here. So let's make that at least the radius of the cutter. Let's make it 0.25. Then this length is kind of that tangent extension, that length. So let's make that 0.1 just so it's something different. You can set the angle. Let's make it 45 just so we see it. And then the normal, I'm going to leave that at 0. Now you can set your lead out differently, or you can keep it the same. Typically it's the same. Alright, that's about all the parameters we can write for this. Let's go ahead and save and calculate, and then simulate. You'll be able to see, I'm going to take this data off and slow this down. I'm going to step into it. You'll be able to see that lead in, lead out. See how it is not starting right where I asked it to start? Now watch it move. Did kind of that little movement there, and then it starts going around. Now check out that extension overlap. In this case it didn't really matter all that much. It did that 1-inch extension way out here. That's just an error. Doesn't really matter, right? If we were to take the geometry, I don't know if I can do this right now. Let's let me see if I can drag this. I'll have to do that another day. There's a way that if you selected your geometry here, but you didn't want it to start right there, you wanted it to start, say, in the midpoint, you could do it. So I'll have to figure that out for you. Okay. Questions there about those parameters? All right. Let's see what else we're going to talk about. Oh. I'm going to simulate this toolpath again, and I want you to figure out in real life there's something wrong with this toolpath. Really wrong. So I'm going to simulate it, and then you tell me what's going to go wrong with this toolpath. Clamps. How did we hold that piece down? You're going to run into clamps. Okay? So there's a variety of ways to skin that cat. I'm going to teach you one little interesting method, which is we don't use very often, it's kind of rare, is if you had a piece that was a little bit bigger than this piece of stock, okay, you could put clamps out here so they're out of the way of the tool running around the outside. And then instead of going all the way through this 0.0787 thick piece of material, whatever it is, you could leave, say, 20 thousandths or so in the bottom. Okay, so you could go like, if it's 78 thick, you could go like 58. Okay, cut this out. And then you could start stepping down by very small increments. So there's 20 thousandths left. You could step down by 5 more and run around. And then 5 more and run around. And then every time you're done, you could take a screwdriver or some sharp piece of metal, some pointy piece of metal, and kind of push down on the floor of that aluminum. As you get very, very close, it'll start feeling like aluminum foil. It'll start giving a little bit. Okay, and then once you get to that kind of foilish feel, you know you're cool and you can stop, you can pull this material out, undo the clamps here, and then you can kind of just snap that part out, kind of like little models that you did when you were a kid. Or you can kind of X-Acto knife that really thin piece or sheet aluminum down at the bottom, and then you can fatigue that aluminum by bending it back and forth and then filing that edge. Okay, remember aluminum foil is like 3 or 4 thousandths thick, so you leave 20 and you start stepping down, you get close to that 3 or 4 thousandths thick, it's just going to be like foil and you can just peel it off. Now that doesn't always work, especially with thin pieces or especially with larger, longer pieces, because the material itself is wavy a little bit on the order of thousandths. So what you could run into is you could, as you get really close, like within 4 or 5 thousandths, you could cut all the way through maybe on these two edges and still have material on these edges. And that way this thing's going to start flapping up and down, and then you'll get poor finishes and poor dimensional tolerance on these sides. So you can't always do this, but if it's small or thick parts, you can get away with it sometimes. So it's a method that you can use. If we didn't use that method, what would we have to do? Which is what you're most certainly going to have to do on your parts, your QB50 parts. What would we have to do? How do we get all the way around this without whacking clamps? What's that? Yeah, but if the clamp, in this case, the clamp's probably going to be on the part. So yeah, you could lift up over the clamps, but you're still not going to be able to machine that edge. Let's say if the clamp was here. There's multiple answers to this problem. You could do something crazy. You could drill and tap these 4 holes in the plate that's underneath, and you could screw this down, and then you could just run around it. So you could do that. It's a little bit of work, but you could do it. There's a more common method that we use, and that is we'll put clamps from one side, and we'll cut only half of the part. Then we'll flip the clamps over, and we'll cut the other half of the part. It's such a common method that I want to show you how to do it. So let's pretend like we had a clamp here and a clamp here. So we can only cut, say, this side out. Okay? So let's go back to this contour. We'll edit. New geometry. This time I don't want to use the Autoselect tool because I want to select these guys. I'm climb cutting here, so that's good. And I kind of want to jog around here, not around the clamps. I'm going to quit right there. So I've got a clamp here and a clamp here, so I'm free to cut here. I'm going to accept this chain and accept this geometry. Now, this is where we really want the lead in, lead out. I don't want to start right on this point. So I really want that lead in, lead out. I have it, so that's good. So let's resave and calculate and re-verify. That's what it's going to do there. See how it's leading in, leading out? Now, I should probably kill that overlap. That's a little overkill there. So go back in here. Change my overlap. Another problem happened. Anytime you reselect geometry, for safety's sake, this CAD program or CAM program, which they all do, is going to set your depth back to 0 for safety. So you're going to have to redo that. Alright, let's save and calculate and simulate. Notice that crazy long inch is gone. And it went around twice. Why did it go around twice? 1, 2. Finish. Remember, we asked it to leave 5 thousandths on the wall and then finish it up with 1 pass. So there's that. Okay, now here's the problem. We've cut that out. Now we want to cut this out, but we got to move the clamps. Okay, if we just write another contour with the same end mill, same tool number and everything, the machine's not going to stop. It's just going to run around, and then when it's done with its finish pass, it's just going to start on this one, just blow right through your clamps. So there's 2 ways to stop the machine. You can either write another tool path with a different tool, because the machine knows you have to stop the machine to change tools. So you could do it that way. Or if you wanted to use the same tool, you have to tell it to stop. And there's a way to do that. So right click, edit in this tool path, go to miscellaneous parameters. It's probably the only one you're ever going to use in miscellaneous parameters. You can go to the parameters list, and there's this one called stop, and you can toggle that to yes, and it'll stop. You could also use this message and type in a message to yourself or your partner that says, hey dude, move the clamps. Okay, you could type that in there, but that'll make it stop. Okay, now we want to go around this other side, but we want to do it exactly the same as we did this one. So instead of rewriting an entire tool path, let's just copy, right click, paste. Now this little star means we've got an uncalculated tool path. What's the only thing we want to change here? We want the same tool, the same feeds and speeds, same flood coolant, same everything except for what? The geometry. So we need to go into here and edit the geometry. I think I stopped right there, so I need to start right there. And I already did this one, so I'm going to stop there. Now remember when I said if you ever change the geometry for safety's sake, it kills your depth. So you've got to redo that depth. And then you're done. Simulate that. Make sense? That's a powerful tool, moving the clamps and then stopping your tool path. You'll probably have to do that on yours. Any questions about profile paths? Okay, next thing I want to show you, which I touched on before but we didn't really go into depth, is adding your own geometry to force the tool to do what you want. So we did a little bit of that, but let's do some more. Alright, so this was an ex-student, maybe 06 I think. It's a good friend of ours, and he has a custom motorcycle, and he wanted to buy this really custom cool headlight for the motorcycle. He wanted to mount it to the motorcycle, so he made this custom mount that kind of bolts to the forks, and then the light bolts into this hole. And if you look at this design, you can, what it is the fork goes in here, and then he's got this piece of aluminum that's cantilevered off here with this slot. And then he's got a threaded hole right here and a counterboard hole right here. So he's going to put a screw in here, and it's going to sit flush. And then as he tightens this down, it's going to bend this cantilevered beam down and crimp onto the fork and hold it in place. Okay, so that's the design. We wrote a drill path. You could simulate that. See the hole? And we wrote a pocket path. You can see it cutting out the circles for the forks. And then we wrote a contour path, which kind of runs around the outside on that side. We didn't go all the way around. Why? Because of the clamps. But I want you to notice something wrong. See anything wrong with that? Maybe it'll be more obvious if we do solid verify. Actually, that's less obvious. Whoops. What's wrong there? Yeah, we bumped into the material. Maybe he wanted that, but maybe he didn't. So the tool doesn't know that that's materials there. It doesn't know. So it's going along its geometry, which was selected. Let's see. Go to geometry and hit show. And you can see the purple line. Oh. See that purple line? So it's following that line. So when it comes over here, it just follows that line, and it's got to get all the way to that point because we selected that point. So you can see right at its center point, it hits that point, but that's too far and it bounces into the material. Okay, we don't want that to happen. All right, so we need to force the tool to not go all that way. And the way we did it was with additional geometry. I'm going to take it out so that you can't see it. So if we start here, that end mill is going to bounce in here. But if we were to draw a line here to here and here to here, it would have to follow that line. Okay. Now there's a couple ways to do it. Notice there's these big fillets, so we couldn't select the geometry up at the top plane. So we selected the geometry at this plane because that line will go all the way around the part. So we're going to select down there. We could draw a plane in on that plane and sketch on that plane, or we can cheat and use 3D sketch. I'm going to go to sketch and go to 3D sketch, which will let me sketch in 3 dimensions without a plane. So I'm going to select this little vertex, and then I'm going to snap, use the SolidWorks snaps to try and snap it across. Hey, oh, you have to put a line in there, dummy. So I'm going to select that, and then I'm going to come over here, and I'm going to try and snap it too. And it's having a hard time guessing what I want to do because I'm looking in weird directions. So we need to look in a direction where SolidWorks can guess at what I want to snap. Where did I finish that line? Uh-oh. I'm going to delete that line. I didn't want that one. So I'm going to come over here, this line. Okay, so now when we tell our tool the geometry we want, we can start here, and it's a circle here. It has to go here, and it has to turn this corner and then start moving along. Okay, now the problem is I made this sketch geometry it's digging into the part, right? So, and that's determined by the length of this line. So we can force that line to be exactly as long there by going to evaluate and measure. Let's figure out how far it is from that face to that face. 0.79 inches. So I'm going to go ahead in my sketch and dimension that line to 0.79 inches, and that forces it to be right on the face there. See that? Now I can select that whole geometry and go around the whole part, and it won't bump into that piece. So just for giggles, let's exit the sketch and let's reselect this geometry. I won't go all the way around for time's sake, but I'll start here and go there and there. Oh, let's just do that. And if I recalculate this guy, probably have to go to levels. Let's say we want to go all the way to the bottom. Save and calculate. And then let's verify it. You see, I'm now not bumping into that edge. So that's a powerful tool, and you're going to need. I know you're going to need that on your QB50 parts. In fact, I'm going to go over that probably tomorrow on one of the QB50 parts, along with multiple coordinate systems. But sketching geometry in order to force the tool to do what you want on top of your original SolidWorks geometry, you're going to need that tool at some point. Questions there? Okay, any questions whatsoever? I don't know if you guys heard, but we have SolidCam available on computers 1, 2, 6, 8, 9, 10, 13, and 15. I posted a news item on D2L in case you forget the numbers, so you have 24-hour access to SolidCam in this lab. We're going to, for the machine sign up, we're going to, we did post it on Drive, but we're going to print out a hard copy and post it on the bulletin board on the shop door so you can just write in on it. If there's any conflicts, I will solve them. And you should be able after today. So you saw how to zero your tools and your XY zeros in your coordinate systems. Remember, this part's going to take a long time, and you only have the next week and a half to do it. I would strongly recommend that you try and set your tool zeros today, either during Open Lab in the 3rd segment or during shop time 12 to 5. If you wanted to even try and write a tool path and attempt to drill or mill, that's fine too. But you definitely know how to do your zeros, so you probably want to get that going fairly soon. Any other questions? I think we're done.